Boa tarde a todos e todas. É com imenso prazer que damos as boas-vindas a todos os presentes, tanto aqui nas imediações da UESC, como virtualmente, a mais uma palestra no Seminário de Matemática, de extensão do DCX, para termos essa nossa palestra no mês de novembro. Tá? Então, para fazer a apresentação do nosso convidado, eu vou dar a palavra ao professor Wesley, colaborador do professor Peter Wong.
Obrigado, Néstor. Boa tarde a todos. Peter, I will introduce you in português. Bom, para mim é um prazer apresentar o professor Peter, né? Acho que é a sexta ou sétima vez aqui em Ilhéus, está quase baiano já, né? Dessa vez, o Peter veio nos visitar recebeu uma bolsa do Fulbright para passar 4 meses no Brasil, em particular na UESC, né? 2 meses esse ano e 2 meses no ano que vem. Então, ele está aqui, a gente tem uma colaboração no projeto de pesquisa e tem aproveitado para participar de eventos, da palestra, e hoje nós teremos a palestra dele aqui no Seminário de Matemática. Vai falar sobre Why do you need to learn calculus and linear algebra? Para terminar, o Peter ele fez doutorado na Universidade de Wisconsin, sob a orientação do professor Eduardo Fadel, uma das referências, vou dizer assim, é uma das entidades que nós temos dentro da topologia algébrica, Eduardo Fadel. And then, eu acho que o Peter pode falar melhor do Fadel do que eu. So, Peter, go ahead.
Ok. Muito obrigado, Wesley. Boa tarde. A pergunta é por quê? Okay? Por quê? E a resposta é em inglês. Desculpa. So, it is good to be here, have this opportunity in Ilhéus, and thank you for coming to the talk, or in the virtual audience, I thank you. I was told to say a little bit about myself, and so I will try a little bit. So let me try. Okay. So here is this is very tough. Okay, so something like that. Now you have rest of the world. So this is China. This is and here is this. Okay. So I grew up in Hong Kong. So there's some other things. Okay, there's something else. Okay, so it's around here. So I grew up in Hong Kong. Then I went to university. Oh, where is it? Okay, it's somewhere here. So this is University of Sidaji Medicine. Okay. So I went to study. So when I was in school, I did not know any linear algebra. I didn't know calculus. Okay? So I learned some, and then I did my PhD also in Wisconsin, and my area of research is so I chose this title to let you know that if you learn calculus and linear algebra, you should learn the subject very well, because you will see that even current research requires mathematics from very elementary level. Okay, so, and then now I'm here. I'm here. Okay, good. Oh. So, algebraic topology. So this has to do with algebra, right? So this is algebra. So this would include linear algebra, or maybe theory, grupo, maybe. Many areas in algebra. So I will talk about linear algebra and topology. What is topology? Okay, so this came from Henri Poincaré. He published a work and he called it Analysis Citus, and you know what that is. It's a little piece. So this is a little piece of analysis. And this became, nowadays, in particular, algebraic topology. So, therefore, analysis. So what's in analysis? Calculus, right? Is it yeah, cálculo. Obrigado. Cálculo. Much more. Okay? All right. So, therefore, linear algebra and calculus. Good? All right. So, let me start. So, you learn something very important. This is around 1817 by a mathematician named Bolzano. Sounds like Italiano? No. He lived all his life in Praga. So very little Italian. Okay. All right. He proved, now known as intermediate value theorem. Okay? So I'll give you a form that is easy to state. So I will do the following. Let's say, let f, let's say from -1 to 1, okay? And this is continuous. Very important, continuous. Now, I make some assumption. So assume that, suppose f of -1 is negative and f of 1 is positive. If you have seen the more general version, you see you can modify this a little bit. Then there exists a point C, and I hope it is okay for me to write this notation. A point between -1 and 1, so that f of c is 0. Now, the idea is very simple. So you have a map from here to the real line, all right? So that -1 is negative. So you will see that if you look at the graph, f is here, f of -1 is here, f is here, f of 1 is here, right? Positive, negative, and you take this, and you will see that at some point it must cross this line, right? Well, if this function is not continuous, then you could have something like this. Right? Like a step function. So, continuous, very important. Okay? Now, this actually, now I'm going to tell you that this is the very first real fixed point theorem in topology. So, from this, I will give you a theorem. So this is the First, fixed point theorem. Okay, f from -1 to 1 to itself. All right, continuous. I think I spelled it incorrectly. Continuous. Then there is a point C in this interval so that it must be fixed. Okay? So this is a mathematics talk. I learned, or somebody said to me in a mathematics talk, you must prove something. So I give the proof because this is simple. All right? So I'll give a proof. All right? So the proof is this. Okay? This is good. All right, proof. So I let h of x to be x minus f of x. Okay? From calculus, you know that this is also continuous. So continuous, very good. Okay. So let's take a look at how we prove this. Okay. So first, if h sorry. If, what do I want it to be? Oh, yeah. If f of 1 is 1, or f of minus 1 equals minus 1, then we're done, right? Well, okay, so otherwise, let's pick your favorite number, right? So pick a number somewhere here, all right? Pick a number x, all right? So what do you get? So otherwise, so you can look at any number, then you can see that otherwise, h at 0, what is h at 0? H at 0 is 0 minus f of something, okay? And f of something cannot be 1, cannot be minus 1, okay? So likewise for, did I say h of 0? Sorry, h of minus 1. Sorry about that. H of minus 1 and h of 1. Let's try h of 1, sorry. Is 1 minus something f of x. F of x is between minus 1 and 1. So at most, something little less than 1. So therefore, 1 minus something less than 1 is positive. Similarly, minus 1 minus even something negative, but not minus 1. Get this. So, intermediate value theorem says h of c equals 0 for some c, but h of c is c minus f of c. So, c minus f of c is 0, c must be f of c. Okay? Good? So let's look at a picture. So the picture is very easy. -1. So let's look at the height. Okay? So here is -1 to 1. Okay? All right. And then you look at also this. You look at the what we call the diagonal. The diagonal is the set of points x and x, right? That's the diagonal. Where's the graph? The graph of f is something like this. That's the graph, right? So if you pick something like this, you adjust this, but this is the graph. Okay? The graph must cross the diagonal. By crossing the diagonal, this point is, on one hand, it is x. But this is the graph of f. So this is, so they must be the fixed point. Okay. Now, let me move forward a little bit. So this is 1817, and this is the same as this. And now, let's move to this is about 1912, something like that. Okay? And you have an interval, one-dimensional. If you take vector calculus, multivariable calculus, you go to dimension 2, dimension 3. In dimension 2, you look at a disk, right? So, he proved the following. N-dimensional disk to the n-dimensional disk. So I will make sure we understand what this disk is. So the n-dimensional disk is the following. So this is the two disk. The two disk is the set of points x, y, such that including the boundary. Okay? So do this for n dimension. And the theorem says, if you have a continuous map, I know what happened. Okay? A continuous map, continuous. Then there is a point in this disk so that it's fixed, right? Is it obvious? I'm not sure. Let's give it a try. Now, for a topologist, a disk is the same as a rectangle, Same as, this, also rectangle. I don't know what other shape you have. How about the shape of the state of Bahia? And here it is, okay? So, yeah, that's right. Okay, so we're here, all right? This is the same as this, same, okay? But if you believe me, let's take a map. What map? A map from the disk to itself, So this is a copy of it, okay? Okay, so this is my domain. Here, this is this, okay? Remember, the map must be continuous. In the one-dimensional case, I cannot break it, right? If I broke it, that means you have to break that apart. Well, in this case, that means I have to puncture the disk, make a hole. So I cannot do that. But I can do this. So you pick this, right? And then as long as I don't break it, it is okay. Right? So this is the image, not exactly. But what do? I will, thanks for Nestor, I'll try this. I don't know if it will work. I hope it works. I will clean it later, don't worry. So I take this, I crumble, it is continuous, and I have to map it back to here. Inside the disk. Inside the disk. You say, well, why is it sticking out? So just do this. It's flat. Okay? It's flat. Right? What does the theorem say? The theorem says that somewhere on the disk must be in the same position as before you map. Somewhere here, I don't know where. This point must be the same as, hard to do, some point here, I don't know where, and its image coincide. Now, if you never heard of this, good, but also don't try to find where that point is, okay? Okay, now, the problem with this is that you have some glue. Okay, well that's okay. All right? This is not entirely obvious. Okay? But the theorem says yes. So, how much time do I have? 10 minutes? Okay. So, I am going to actually tell you about linear algebra a little bit. Okay? So, I'll skip something. But now let's go to linear algebra. So I'm going to speed up just a little bit. So in my abstract, I will discuss, I think, the most important theorem in, I should say, early algebraic topology. And that is around 1921 by Lefschetz. Okay? He says that X be some nice enough space, F is a continuous map. And then he associates to F something from linear algebra. And then he said, if this is not 0, then f of c equals c for things in there. So you can see this is some kind of theorem like this, except this x can be quite general. So where did he obtain this linear algebra? Now, I'm going to give a different proof of this. But the idea is similar to what he had. And this comes from another mathematician, Hopf. But I will tell you how to view this theorem. This is so-called the Lefschetz fixed point theorem. So pick your favorite space. I don't know if you have donuts here, but okay, pick your donut, just the surface, okay? And then you can see that sometimes you can, what we call, triangulate. And so on. Triangulate, okay? So what does it really mean? Well, here's the idea. Well, Dn, what is Dn? When n is zero-dimensional disk, 1 point. How about this? But be careful. You must include the inside. So I'll draw to 3. But also the inside. Okay? So these are called simplices. Okay? Now, you can sort of see how to do this. In this case, the dimension is 2, right? So you only need 0, 1, and 2-dimensional things. Then you can think of it as having a lot of simplices, that they are what? You know, that are put together like that, and then it's made out of rubber, and you put on the surface. Okay? All right. Now, so such a space, such a nice space, sometimes we call it a finite simplicial complex. Okay? Made up of these things. Okay? Now, if I have a continuous function, we can approximate. When I say approximate, that means I can use very small triangulation, right? Very small ones, in such a way, even though the function can be very wild, but when the things are very small and it is continuous, so it moves just a little bit, okay? So we can approximate f by a simplicial mapping, right? So that a simplex is mapped to another simplex. Now, let me warn you that it is possible that I have a map that collapses this to a vertex, but it is still okay. It is still okay. All right. So far, so good. I have this. All right. Good. Now, a little bit more linear algebra. Well, I have not told you the linear algebra. Okay. Now, take n to be 2-dimensional. So what are these? Well, the space is not infinite. So you can have only finite number of vertices, finite number of edges, finite number of triangles, right? Finite. So but finite. This is the dimension. Dimension, I have 5 vertices, 10 edges, and so on, right? Okay, here's a linear algebra. This is a vector space with basis whatever it is, all right? This is a vector space with this as a basis. This as a basis. Okay? We all know that, how to do that, I assume. Right? Oh, okay. So this function gives rise to a, in each dimension, well, what kind of maps do we study in linear algebra? right? If you have a linear transformation, I have basis, a matrix, right? This is I, so T sub I, right? Vector space, linear transformation, matrix. Good? All right. So to finish my talk, I'm going to tell you exactly what happened, right? In dimension 0, you look at the following. You look at the trace of the map. Well, this is not much. 0 dimension. Okay. In dimension 1, you also look at the trace of this. And you look at number 2, dimension 2, you look at the trace of this. Okay? And then I'm going to say, oh, whatever dimensions I have, let me put them together. This is the dimension. It goes up to, in this case, 2, right? Or in general, whatever dimension. Okay. Okay, now what? Well, if this is 0, what does that mean? At least one of them is non-zero. Okay? Do you agree? If this is non-zero, if this whole alternating sum is non-zero, one of them has to be non-zero. Okay. Aha. I. All right. So, Nestor, what should I be? I know it's the dimension. What dimension do you like? 2. Good. So, take dimension 2. What is this matrix? Suppose I have 5 two-dimensional simplices, okay? So I have, this is 2, first, second, right? Okay. But this map is simplicial. What does it mean? It must send a simplex to a simplex. Well, from linear algebra, how do you write the value of the matrix? Each one is a linear combination of the others, right? What is the trace? The trace is here, right? So, if this is not zero, the trace of this matrix is not zero, that means something here is not zero. Now, what does that mean? That means this map sends the fourth, this simplex, to itself. Say, okay, well, why is it good? But what is a simplex? A simplex is like this. It's a disk. I have a continuous map from a disk to itself, therefore I must have a fixed point. Okay? Now, I did not tell you all the details how to set things up. But this is roughly how it works. Since I don't have time, Lefschetz define something in homology, if you know what that is. So the final remark is, why is this -1? Let's think about it. I'll give you 15 seconds. As I said, this is not the Lefschetz number, but this trace turns out to be the same as the Lefschetz number. But this -1 turns out to be the following. That if you take f to be the identity function, what does it mean on your trace, on your matrix? Right? How many? As many as there are, let's say this is Q simplices, right? Good. Take Q to be 2. So actually, 0, 1, and 2, right? So let's write this. The trace is now the number of vertices when Q is 0. The trace is now the number of edges when Q is 1. And number of faces when Q is 2. This, for the identity map, is, I just said, when Q is 0, it is positive. So it's the number of vertices minus the number of edges. So this is edges plus the number of faces. Especially in early works, let's say in the works of Euler, when you do graph theory, you come across this. So it has a lot of connections. So I hope, I know I did not give you all the details, but in some sense, this is where many things begin. Calculus, linear algebra, and then you start from now. And you start, all right? So with this, this is finished. So, muito obrigado.
Vou falar aqui. Bom, alguma pergunta? Pessoal daqui ou pessoal de casa, né? Nossa internet.
Yes.
Have you already teach the subjects you told us today in a university for students in graduation, or just for teachers or something else?
Okay. Okay. So this will be not in a regular class. Here's the reason. If you teach a real class, you have to give details. A lot of this require, such as, how do you prove the higher dimensional Brouwer fixed point theorem? The linear algebra will require, and this actually is due to Hopf. This is called the Hopf-Trace formula. So the students will need some background in a little bit of topology, a little bit of linear algebra, a little bit of analysis. So in a course, if it is only for undergraduate, or you call it graduate, it will be maybe advanced students, maybe. But in graduate level or postgraduate, yes, you certainly can do this. But at the first few years, it's hard to have the details. Okay. But this gives you the motivation to learn. Oh, okay. By the way, if you have questions, you must ask Professor Weston. So I almost forgot. This is the main reason. Is all of these, he understands, so he knows what kind of details you need. So if anybody interested, ask it. So I mean, right now I'm just giving you the main ideas.
I know. I got it.
Yeah.
Thanks.
Se alguém quiser fazer pergunta em português também, pode.
Ask it.
Mais alguma?
Como se faz essa conexão entre a função e essa versão que vai permitir calcular o traço? Mas aí depois eu te pergunto.
The details function.
Yeah.
And this function that we use to calculate the phrase.
Yes.
She asked about the inducing map and the chain level.
Yes. So that comes from the fact that you can think of, especially if it is simplicial. Then remember that vector space, right? That vector space, a typical element is of the form A sub I, whatever the dimension is, right? And then the map that it does is that, well, F now sends this to what? If it is simplicial, then you can see that, this will send a simplex to a simplex. It may be a lower dimension, okay? And then you show that you have a linear transformation in terms of, these are vectors and so on. So that's just a little bit more, not much. Good.
Mais alguma pergunta? Néstor, você tem algum aviso? Okay. Oh, thank you, Peter. Oh, nice talk.
Muito obrigado.
Let's go. Vamos agradecer novamente, Peter.
Thank you. Good.
Agradecer ao pessoal também da transmissão pela participação. A gente já vai encerrar. E no dia 6 de dezembro teremos a palestra do professor Claudemir, que está aqui presente, mas ele não vai querer aparecer na transmissão, então fiquem ligados que no dia 6 a gente vai fazer mais uma transmissão ao vivo. Obrigado. Thank you very much, Peter. It was very, very, very nice.